Great, thank you. So, hi, good morning. My name is Georgiana, and I will talk to you about Vecpar, which is a new portability parallelization library. So, first of all, I just briefly want to mention why we started to build a new library when so many others are already available. And then I will talk a little bit about the Vecpar library and walk you through a very simple code example. And after that, we'll just look at the evaluation that we did on a very simple use case from track reconstruction and conclude with some observation that we had. So the motivation is very clear. We all know that the data acquisition will increase in the new Hilumi. So more events will come and the degree of complexity will also be increased. Nevertheless, we need to somehow increase the efficiency of the way we exploit our hardware resources, because otherwise we will not make it to the new era. As you can see from the plot on the right, the continuous lines show the budget lines that are available for the next roughly 15 years or so. The dotted blue line show the conservative R&D methods, which include maintaining all the knowledge inside the teams and dedicating the same efforts and the same technology and the same hardware in order to keep up, while the green while the red line shows more aggressive R&D methods, which means probably new algorithms or more dedicated time for software and computing and so on. As you can see from this, we actually need to go to the aggressive R&D methods in order to meet the requirement budget. In the same time, the architecture is changing nowadays. So most of the larger supercomputers use accelerators to boost their performance and also reduce the electricity consumption. And so far, until earlier this week, I think NVIDIA was the most highly ranked GPU vendor in top 500, with Summit and Uvels, which were US and Europe's most powerful supercomputers, having NVIDIA GPUs. As of 2 days ago, the new exascale computer is Frontier, the most powerful in the world, and it has AMD GPUs. And others will also follow the lead. So Lumi, which is currently the most powerful in Europe, or El Capitan will also use AMD GPUs, while Intel GPUs are going to be used at Aurora supercomputer, which is currently being built at Aragon. So in this moment, portability is very important and probably more important than ever. Of course, the software ecosystem tries to keep up with this. So there are many solutions in order to target these accelerators and use them for running our code more efficiently. There are three main categories of doing so. So first of all, we can use the language extension and proprietary frameworks like NVIDIA CUDA, probably this is the most famous, but also there's AMD HIP or Intel One API. The problem with this is that they offer limited portability. So for instance, you cannot compile a CUDA program on ARM, or limited portability on ARM, no portability on NVIDIA or AMD, and so on. And you also have to rewrite most of the code in order to fit the new language. And I don't say about just source-to-source translation, but also rewrite the algorithms in order to make use of the parallelism. The second approach would be to use compiler directives. I think this is the most invasive method. OpenMP and OpenCC are just a few examples, but again, they offer limited portability when discussing single source, because yes, a C++ code with OpenMP can run on both CPU and GPU, but you would need dedicated progmas to target CPU and GPU. So again, the code will diverge a little bit. There's also the portability libraries like Cocos, Alpaca, and the newest addition to the family is NVIDIA StudPar library. They offer a great deal of portability, with the downside that the code needs to fit their abstraction. So the code most likely will have to be rewritten in order to fit this. Alpaca and Cocos are almost comparable in terms of effort of porting, while StudPar could be a bit easier to use in the code, but at the moment might not be as mature as needed. So again, choosing the right solution depends very much on the application and what compromise are we willing to take. This is why we thought about designing a new library which will somehow fit some of the gaps that I mentioned on the previous slide. So we have a new set of requirements. The idea would be to have a library that is easy to use, that is plain C++ code, does not require the programmers to learn new languages like CUDA or new paradigms like Cocos. and would require limited code changes to be adapted. You don't have to rewrite your entire code. Also, the idea would be to abstract away the notion of architecture. Ideally, the person who writes the code shouldn't care where the code is being executed, on a CPU or on a GPU. And to do so, we would like to ensure the usage of single source code. And also, if this is not possible, maybe for platform optimizations, then the code that is extra needed could be generated automatically. We want Clang to be able to compile, so no special compilers here. We want it to be portable. Of course, at the moment, works on shared memory CPU and NVIDIA GPUs, but can also be extended to new architectures, and we're currently working on that. And it could also potentially run on big data platforms. If there are some Google Cloud or AWS accounts, we can also test on that. And also, of course, not the least important, we want to guarantee some improved performance when compared to the initial sequential version that we started, and ideally with no penalty over native parallelization solutions. So we designed Vecpar having this in mind. So before walking through the library, I just want to tell you a few concepts of data parallelism, because Vecpar relies heavily on these. So data parallelism obviously means executing the same task for several elements of the same collection in parallel. As familiar for everyone, probably the OpenMP parallel loop is an example. Also, it requires the data to be partitioned and distributed among the workers. Ideally, this should be some sort of a round robin, so each thread would have almost the same amount of work to be done. And the workers could be anything, could be CPU threads, could be TBB threads, could be CUDA threads, or whatever. Also, if we want to use the GPU, we want to offload the computation, then there are two preconditions that have to be met. First of all, the function pointer of the actual code has to be copied to the GPU, and also the data that is used for the computation needs to be available on the device. Well, what Vecpar does is somehow abstracts all these from the code and handles both data distribution and host to memory, host to device memory transferred and back out of the box without explicit instructions. Vecpar builds on map filter reduce paradigm from functional programming. So very briefly, a map function is a function that applied on each collection would produce another collection of the same size but of different elements. And an example of that could be maybe apply a function that is called to space points, and we get a collection of measurements, and we will obtain a collection of space points. A filter is a function that will filter the collection, obviously, based on a predicate. So in the end, the collection, the elements that remain in the collection are only the ones that satisfy this predicate. And we can imagine a scenario where we want to filter maybe the space points that are above a given threshold. And reduce is an operation that gets a collection and reduces to a single result that could be initialized or not. So maybe if we want to gather a list of volumes while we were passing through different space points in the propagation, we can do so with a reduce function. So for Vecpar, we enable a couple of basic and some composed algorithms. So we have a basic map, a basic mutable map, which actually works on the same data that it received, a filter and a reduce, and some more composed algorithm like map reduce or map filter. Behind the scene, there's the data model that is handled by Beckman Vector, and the storage location that can be host memory or managed memory, and also some parallelization strategies which can be OpenMP on CPU and CUDA on the GPU at the moment. If we want to execute this code on different platforms, the only thing that we need to do is just compile it for different architecture. But in the end, we have the same C++ code, but it gets compiled once for CPU and the second time for the GPU using Clang. Let's see some very, very basic code examples. So we've been working with the Runge-Kutta-Nystrom integrator, which is used to estimate the position and the momentum of charged particles by integrating the equation of motion. This is a very compute-intense algorithm due to the numerical integrator, but it is ideal for parallelization because it can be invoked in parallel for different tracks since the data is independent. So we used a simplified version of this algorithm. And when I say simplified, it's is simplified because it uses a fixed number of integration steps, so it doesn't wait for a specific convergency epsilon or something like that. It runs a fixed number of integration steps, and I built the example on the code existing in the DETRE project. Böhmke introduced to you the DETRE project yesterday, so you might have a few ideas on how it looks like. So the basic CUDA code that actually Böhmke wrote for the DETRE project was looking like that. So there was a kernel that had received a vector of tracks and the magnetic field. And for each track, we get the ID of the CUDA thread that executes the thread. We make sure that the memory is available on the GPU. We make sure that we don't work on an element outside of the vector, and then the code that is highlighted in blue is the actual Runge-Kutta calls. So defining the stepper, have a fixed number of steps in the forward direction, flip the trajectory, and then have the same number of steps in the backward direction. I will not go into what the step is actually the implementation of the fourth order Runge-Kutta, so the 4 tangents computed for each step. Now, if we look at that implementation and report it to use Vecpar, I again highlighted the same code, copy and paste it from the previous slide, and I just fit it into a function called map with a specific signature and wrapped it into a data structure. And this is all the code that you need that can be executed on both host and device. As you can see, there is no index-based calculation. There is no notion of CUDA, which thread executes what, no notion of how to access the memory on device and things like that. It's all abstracted away from you. You just have to figure out how to write the algorithm, and everything else it's somehow hidden behind the scene. So let's evaluate these results. To evaluate the implementation, we looked at simulating 10,000 tracks that cover phi and theta as described here, starting from the origin position. For each of these tracks, we compute 100 integration steps in each direction for each track. And another simplification that was done is that the magnetic field that is used is a constant one of 2 Tesla in the z direction. Also, we looked at different backends for DETRE. We look at the CMAT, so the mathematical backend that we use to hard code linear algebra function, and the one that relies heavily on the eigen library. On the same time, we tested on 2 different environments. First of all, on a CPU with 16 cores and with an NVIDIA GeForce. And second of all, on a cluster node with 40 cores and an NVIDIA V100. And with absolutely the same CUDA drivers and Clang compilers, and everything else stays the same. So let's look at the CPU results first. What I plotted here on the left is a comparison that I did in between the following implementations. So first of all, the sequential implementation on the CPU is the starting implementation that I started with. Then I manually parallelized it by adding OpenMP pragmas to this code. So I made it parallel, and I obtained the second implementation here, which is the OpenMP CPU. And the third value is the Vecpar code that is very similar to the one that you've seen on a couple of slides ago. And as you can see from this plot that shows the mean and the standard deviation of the wall clock time, we can obtain very good performance in comparison to the initial version, and actually a little bit better than the OpenMP one. On the image on the right, I plotted the strong scaling evaluation. So I looked on how increasing the number of threads would impact the wall clock time. So on the x-axis, you see the number of threads, so 1, 4, 8 up to 40, and on the y-axis, I plotted the logarithm of the wall clock time. And also, so here I plotted only the parallel version, so the OpenMP and the Vecpar. And I also, the gray line is the ideal scaling, which is mathematically computed based on the actual architecture. So you can see that our solution scales pretty well and almost identical to the code that was hard coded with the pragmas. Looking at more speedups. So in this plot, I plotted the speedup in comparison to the initial sequential implementation that you can see in blue for both backends, so CMAT and Eigen. What you can see in orange is the OpenMP version, again, my hard-coded version, and what you can see in green is the Vecpar one. So you can see that we can obtain the same or slightly better performance than the actually hard-coded parallel versions. When we move to the GPU, the situation is a bit different, but not so different. So what I plotted here on the left are the results for the dual clock time obtained with the CUDA implementation that I've shown you on a previous slide, compiled with NVCC compiler, and the Vecpar code, which again I showed you on a previous slide, compiled with Clang for NVIDIA GPUs. And there are two measurements because I looked at on both environments, one the gaming GPU card and the V100 card. And as you can see, the measurements look pretty nice, so we can obtain almost the same or slightly better performance than actual native CUDA code compiled with NVCC compiler. To mention here that this is not necessarily the merit of my library, but the Clang compiler does an impressive job in compiling C++ code to NVPTX. On the right, it's the same plot, but with fastmath flags enabled for both compilers, both NVIDIA and Clang. And again, now the results are a bit more tied together. Nevertheless, I think we can safely say that we can ensure comparable performance to native implementation. To aggregate, actually, we're not there yet. So looking at different precision, I plotted here the wall clock time when when the computations are done in simple precision and in double precision. And as expected, the double precision takes a little longer than the simple precision. Nevertheless, the Vecpar implementation is always at least as performant as the CUDA one, if not slightly better. Now, to aggregate everything, so in comparison to the initial implementation, which is on this plot in blue, I plotted in orange the CUDA. Actually, this is not CUDA, this is actually OpenMP parallel version. I'm sorry, it's a mistake on this side, on this slide. And no, actually here it is CUDA NVCC and Vecpar on GPU. And again, this shows that the Vecpar speedup is slightly better than the actual native CUDA implementation. And of course, in comparison to the initial sequential implementation, we can obtain a speedup of up to 38 times. In this plot, I showed the initial implementation again in blue. In orange, we can see the CPU implementation, and in green, the GPU implementation. Bear in mind that the Vecpar's implementation are behind the scene the same C++ code. The only difference is that they are compiled for different backends. And yet, with the single source code, we can obtain a speed up well above 60 when we talk about simple precision, and around 40 when we talk about double precision, which is a bit, it's expected because a double number of registers, and the data takes a double amount of bytes. We also did some extreme load tests. So we tested with 1 million parallel tracks. And what you can see in this plot is, again, the initial version, the sequential implementation in blue. Then in orange and green, the hard-coded OpenMP version versus the Vecpar implementation. And in red and purple, the CUDA compiled with NVCC and the Vecpar compiled with Clang for GPU. The CPU here, the CPU speedup here is a bit limited because we run on a platform that has only 16 threads. So it will probably not be able to overtake this number. Nevertheless, the GPU code shows a speedup of almost 70 when running on general purpose GPU. This is a gaming GPU, but it's a general purpose one. On the right here, I plotted some statistics about the GPU kernel as shown by the Nsight compute tool. So we obtain almost as maximum occupancy. So the theoretical occupancy for this kernel is around 66%, and we can obtain 65. So that's very close to the maximum theoretical occupancy. Also, the execution time for one kernel is very low. It's in the order of 108 milliseconds. But keep in mind, this is for computing 1 million tracks. The memory throughput is roughly 130 gigabytes per second. And again, this is not a cluster card, but a GPU card that can be found in a laptop. And we also used very much of the cache. So we have a very good cache hit rate, above 80% when we're talking about L1 cache and above 90% when we talk about L2 cache. So to aggregate all the plots that I've shown you, I can say that for this specific example, for the simplified version of the integrated that we tested on, we can obtain speedups of up to 70 times over the initial sequential implementation using only one code base, but compiled from different platforms. Also, Vecpar shows comparable results in comparison to the hand-tuned OpenMP or CUDA implementation, while Vecpar has only one source implementation. Just to give you a very brief update on where the status of this library is. So at the moment, it is everything is public on GitHub. It's open source. It supports CPUs from x86 and NVIDIA GPUs. Also, we use VecMem library to handle the data structures and the memory allocations. At the moment, only VecMem vectors are supported as iterable collections for parallel algorithms, but we're working on supporting jagged vectors also, and this will be able to happen very soon. Also, managed memory is fully supported for both backends, the CPU and the GPU one, while the host to device memory is supported with some restriction. The restriction being is that the objects that we want that you need to transfer it on the GPU can be default constructible. And also the library is fully covered by automated tests using Google Test infrastructure. Again, Vecpar is very in early development phase. We've been working in the last few months, so yes, just expect to have some missing pieces at the moment. What we want to focus on next is offloading a full chain on GPU, because at the moment you can run several algorithms as composable algorithms on the GPU, but with the downside that after the kernel is being executed on the device, the results are copied back on the host, and maybe this is not actually the best performance ever, so we want to chain them all together on the GPU. Also, we're working on supporting more complex data types like 2D vectors that will be represented by VecMem jagged vectors. And also we are working on some automatic performance optimization. This will be an extra tool that you can run on the code before actually compiling. And also maybe we can think about targeting new backends, maybe with HIP or SQL or some other more generic approach. Again, suggestions and contribution are highly welcome. Just please email me if you want to contribute in any way. Thank you.
Thank you, Georgiana. I hope you heard the clapping in the room. We are open for questions here. First one. Please state your name also.
Yeah, hello, this is Michelle. These are very nice numbers. I wonder a bit when you have a Romeo code that isn't quite so ideal. So if you have a non-uniform magnetic field and your tracks go to different areas of the field, do you know how it scales? I mean, do you lose a lot compared to your ideal situation?
We haven't tested that yet. Actually, in comparison to the talk that you've seen from Bianchi yesterday, so I hope that we can integrate Coffee very soon, which is a library that probably will help a lot with reading the magnetic field in different points, and hopefully this will not be a huge penalty performance, but we haven't checked that yet.
So just to add on, what we have checked is with the same basically code base, how often we have to, in the adaptive Rumikuta approach, evaluate or redo the step because the first step wasn't good enough. And even with the Atlas magnetic field, which does have quite some inhomogeneity, the number is not that bad. So it's really up to 1, 2, 3 maximum tries for a track. So there is divergence in the system, absolutely. I think that's a perfect tool to measure this. Yeah, I think that's really a good follow-up. Was there a question on Zoom? Let me quickly check.
Yep, there's one.
Yep. Here we go, Heather.
Hey, Georgiana, I had a small question back on slide 22.
Yes.
Yes, I was looking a bit, especially at your double precision for the eigen, where I see that it gets slightly worse on the GPU there. I was curious if you had a chance to look into that.
Well, not at the moment, but I briefly discussed with someone from LLVM today, and apparently there are a lot of benchmarks that we can run in order to see exactly how the code is being built for different architectures, and they cannot guarantee necessarily that the code will be faster or slower than the NVIDIA, but based on a lot of tests that they have done so far, is that they could ensure comparable performance. So I think it's somehow related to some performance optimizations that are done differently for eigenstructures than from the backend that we wrote ourselves. But I haven't looked into very much details on that.
Thank you. Any more questions? If not, we're gonna thank Georgiana again.
Thank you.